So the paper that I'm talking about looks at the implications for economic policies of econometric models of climate change. And it's jointly with Jenny Castle, Jürgen Durnik, and Felix Prettis. So climate change is obviously driven by economic behavior. So climate time series share many of the properties of macroeconomic data. Econometrics can model observational records and evolving processes subject to abrupt shifts, which we call wide-sense non-stationarity. So methods for modeling wide-sense non-stationarity include the well-known co-integration for stochastic trends, indicator saturation estimators for outliers, breaks, and shifts, model selection when there are more candidate variables than observations by a variant of machine learning. We can retain theory models unaffected by selection, although it will affect their parameter estimates, but all the variables will be retained, and we can stringently test. But to succeed, climate policies must be based on sound analyses embodied in robust models backed by solid empirical evidence, which naturally has to take account of wide-sense non-stationarity. So here's some typical series. This is global log CO2 since 1958. And as you can see, the trends change quite a lot. Indeed, they change more often than one would like. That's what it would look like if the early trend had persisted. Global surface temperature anomalies have been changing radically, decreasing until the 1930s, which indeed is reflected in books about climate at the time, such as Hubert Young. And these look a bit like economic time series. This is the log of UK productivity from 1860 to 2020. And as you can see, the overall trend line is a useless description of it. It's changed so often, you need very many separate trends. And UK CO2 emissions equally embodies a vast amount of high wide-sense non-stationarity with trends that go up, vast oscillation in the interwar period, and trends coming down quite sharply recently. So this is a summary for those of you who only want to stay in a little bit. Humanity can easily alter the Earth's climate, and worryingly, climate change in the past has caused all the great extinctions. Climate data are highly non-stationary, but recent tools can model them. Models that we've built of the 800,000 years of ice ages identifies the causal role of CO2, and then we can forecast 100,000 years ahead because it's only driven by known orbital data of the planet Earth around the Sun, and we can look to see that at 400 parts per million, where we're already past, we'll have a near ice-free planet over that period. That implies extreme weather, which is dangerous to life. High wet bulb heat kills people, powerful cyclones kill people, coastal and inland flooding kills people, and longer droughts kill people. We have to take care. So it's imperative to get to net zero emissions quickly. Now, to understand how fast it can be done, we have a model of UK CO2 emissions, which shows rapid and large reductions, yet real incomes grew despite stagnant productivity. And I'll explain how we resolve that paradox. But if we're going to have 100% renewable electricity, we have to decarbonize transport by something like modular graphene nanotube units, which will give free storage if we have an intelligent grid. So I think that's the route to go in getting out of the COVID crisis. We've got to tackle greenhouse gas emissions from housing, construction, and as Claudio mentioned at the end of the last talk, agriculture and waste. They all need dealing with, and we have put forward a strategy that integrates all the units of removing fossil fuels from an economy to get towards net zero. We'll never get exactly net zero because some simply cannot be removed, like chemical processes, but we also could research net CO2 absorbers of various kinds beyond just carbon capture and storage. So this is the talk. Can humanity change the climate? Yes. Can we study such processes? Yes. What do we learn from Ice Age glaciation over the last 800,000 years? That the Earth today is very different from what it looked like over that period and could be ice-free. But early on in that period, we had several episodes very similar to ones that are occurring now, but at much lower temperatures and CO2 levels. Modeling CO2 in the UK shows it can be done, and the policy implications to moving rapidly can be done, maintaining growth, and I'll draw conclusions. So we know from long-run data from fossils and air trapped in rocks, formation of fossil fuel deposits, ancient tropical forests, repeated glaciations, the Earth has had a huge range of past climates. It's seen very cold from a snowball Earth to very hot in the Carboniferous period. Life has survived such great changes and thrived in very different global temperatures, but en route, huge numbers of species went extinct from climate change. And change is the key word here, even if long after new species evolve and adapt to the new environment. So this is the fossil record disappearances, the extinctions timeline at boundaries with the various big great epochs, Ordovician, Devonian, Permian, Triassic, and Cretaceous. And we're now into the Anthropogene great extinction, and we better beware what we're doing. Now, somehow the top line seems to go off the screen. I'm not sure why. First of all, Earth has almost no water. Yes, you see Attenborough and a wonderful blue Earth, but actually the oceans are incredibly shallow. And this sphere is all the water in every source on the Earth, from the seas, the rivers, the lakes, the ice sheets, the glaciers, everything. That's all we've got, folks. Can we boil that? Can we turn it into carbonic acid? You bet we can. And that, if you can see it, is all the fresh drinking water on the planet. There's not much. Likewise, there's not much atmosphere. It's no thicker than a sheet of paper around a football. And that's it. You can see it very clearly, how thin it is relative to the Earth. Now, in 1856, Eunice Foote already showed that a flask of CO2 heated greatly in the sun, whereas those of water vapor and dry air did not. CO2 is the cause of global warming. Climate change causes great extinctions. We're in trouble and we need to deal with it. If we look at our CO2 levels relative to those pre-industrial over the Ice Age, the Paleo record, it goes from 180 to 300 parts per million, and I'll explain what role that's playing. Now it's above 415 parts per million. And to link back to the units that Irene used, 1 part per million is 7.8 gigatons of CO2. That's one large quantity, and it's still rising. Sea level's rising, and it's rising ever faster. There's the trend line up to 1940, way below where it is today, and it's continuing to accelerate, already up at 3.4 parts per million, and getting faster, will cause a lot of coastal flooding, but millions of people, indeed hundreds of millions, live in coastal cities. Now, all this is due to Britain inventing the Industrial Revolution. There's startling consequences 250 years later. Real income levels are 7 to 10-fold higher per capita around the world. Many killer diseases being tamed, longevity is roughly doubled. It's not been even across countries, but that is something that is separate and can be dealt with. It depends a lot on the institutions and the timing at which it was introduced. But the cost has been this huge rise in CO2 levels, which is still accelerating. Now, notwithstanding Paris and all the NDCs that people announce, it is still accelerating, not just growing. The Arctic's warming much faster than the rest of the planet, but the rest of the planet's warming. And worse still, the ocean heat content is rising very dramatically in recent years, even down to 2,000 meters. So we need methods of analyzing such changing data. And I'm going to consider not co-integration, which is very well known, but 5 saturation estimators for dealing with outliers, location shifts when the level suddenly jumps, trend breaks, parameter changes, and designed indicators that we've published on for volcanic eruptions or the COVID-19 slowdown, which has caused a big jump downwards, I'm glad to say, in, for example, nitrogen oxides. Now, I'm only going to give a very brief illustration of these because they're moderately well known, but not totally widely. Impulse indicator saturation, IIS, creates a set of T impulse indicators for T observations. Each indicator is 0 except for 1 at 1 observation. Putting all the indicators in at once would give a perfect fit and you'd learn nothing. But if you put them in blocks, then you can learn an enormous amount about the properties of your data. First, under the null, that it's simply an IN, independent normal, 0 sigma squared distribution. Imagine including the first half of the indicators and the intercept. Record which ones are significant, Remember, the parameter estimates are unbiasedly estimated from the second half, because all you've done is dummy out the first half. Alpha, which is your significance level, times t over 2 indicators will be selected on average at significance level alpha. That's standard probability theory. Now omit the first t over 2, for the other half, record again, combine them, and select. We call the null retention frequency after this stage of selection the gauge, and the gauge will be roughly alpha if you set a significance level of alpha. So what do we know? We know a great deal that for a constant parameter model where the regressors are orthogonal to the errors, that y is generated genuinely by beta prime times z's. Z is n by 1, n is much less than t under the null of no outliers. The limiting distribution of the impulse indicator saturation estimator beta tilde is normal, despite more candidate variables than observations. It converges at root t, the standard rate. It converges to a normal. The normal is centered in the true value beta, and there's a variance of the kind you'd normally recognize, sigma squared epsilon, capital sigma to -1, but it's multiplied by a matrix omega alpha, which is the measure of inefficiency from having done this. There's a small loss, but in general, omega alpha is equal to 1 minus alpha to -1 times a unit matrix. So it's very small. If you set alpha at 1%, you lose 1%. If you set it at 0.25%, you only lose 0.25% in efficiency, despite the fact that you've tested for breaks, data contamination, and outliers everywhere in the sample. It's really inexpensive to do this. Step indicator saturation accumulates impulse indicators. Trend indicator saturation accumulates the step indicators. So CIS deals with step shifts, TIS deals with trend shifts. If you combine these, for example, IIS and SIS, you get what Neil Erickson called supersaturation, which can be very helpful, as with the UK, where you're facing a mix of outliers and location shifts. The combined indicators are perfectly linear because CIS are just accumulation of IIS, but not when you enter them in blocks. So you need to set the gauge at roughly twice, set the target level at roughly twice what you do for either alone. And that accumulates if you also add TIS. And we know that overfitting is a bad idea, but you can set alpha sufficiently tight because remember, you can retain all the Zs without selection while selecting over all the indicators, however many you put in, at really tight significance levels. Now, we also find deterministic trends in many empirical settings, but it's extremely unlikely that the same growth rate would be maintained over long periods. And I showed you the graph for the log annual UK productivity since 1860, measures as output per worker per year at constant prices. And if I go to the graph, the one I first showed you, which is this one here, the overall trend is a hopeless description of what happens in a world of changing trend lines. And yet I see many people calculating things like excess demand as a deviation of GNP from a trend, where the trend might have nothing to do with what's going on. Indeed, you can just about see F86 trends. They're not very good either, and they completely miss what happens from 2010 onwards, in fact, 2008 onwards with the Great Recession. If we use TIS to select, we get a good description. I've only used TIS, so it obviously is some of them very short to pick up what are actually the Great Recessions after the First World War, after the Second World War. Notice we didn't have one after the American Great Recession in Britain, and it immediately picks up the flatlining of productivity at the end of the period. And that was selecting at 1 in 10,000, right? So a minute chance of retaining for 200 observations anything that is not genuinely significant. To implement multiplicative indicator saturation, each explanatory variable in the model, xt, is multiplied by every step indicator. So you get huge numbers very, very quickly. And you might think this can't possibly work. Indeed, I told Kitov when he was working on it, it couldn't possibly work, and then he showed it could. So you can't always be right in your intuition. And to see why it can detect parameter changes despite massive numbers of regressors, consider a situation where you knew that there was a shift date in a parameter beta at time t1. Knowing where it happens, you can fit a separate model up to t1, and then after T1. And that will deliver estimates of the different parameter estimates. Well, using multiplicative indicator saturation, we'll select that split, should find the correct indicator or one close to it, albeit with added variability. But if you set it at tight significance level, you won't have too many null significant ones. Now, we've done a lot of analysis of these methods, and recently we've managed to summarize them all in one very simple formula as to what they do, only for the split half method, where you do the first half, then the second half. Because once you start using model selection, obviously the result depends on how good the model selection algorithm is for finding the underlying outcome. But every one of them can be expressed as the error at time t divided by the variable at time t minus the error at time t plus 1 divided by the variable at t plus 1. This is not using the future. This is simply because we're accumulating from the past. If z could be 0, these would be highly erratic. But in fact, the t-test on them will not be erratic because it scales it out in the way that t-tests do. The non-centrality parameter won't be huge if there is a shift, and it'll be much smaller than the known date, but as you do model selection, you'll get much closer to the outcome of the known date value. We've shown that many times in simulation. So now we can reinterpret that step indicator saturation is miss for the intercept, trend indicator is miss for the trend, but both would have low potency for changes in coefficients of mean zero stationary variables, as Mike Clements and I have shown in earlier work. So that's how we're going to tackle the problems. So let's look at ice age glaciation over the last 800,000 years. Right, the discovery of ice ages by Louis Agassiz in 1840 explained previously puzzling features of the Scottish landscape, which is very heavily marked by glaciation. James Crowell in 1875 gave a theoretical mechanism for why ice ages occur by showing that variations in the Earth's orbit would generate them. And he calculated a timeline, which is quite remarkable in a fold-out chart, which goes over about 7 pages. Not exactly correct, but remarkable at the time. He showed that the changing albedo of ice coverage explained why there was a very rapid switch between glacial periods. Now, very rapid in this context is 25,000 years, right? That's still only a quarter of the time in the Earth's orbit around the sun. His research was amplified by Milankovitch, after whom these cycles are now named. And he showed that the eccentricity, obliquity, and precession of the Earth interacted to cause differences in solar radiation at different latitudes. And what matters are cold summer maxima rather than very cold winter minima. The three main interacting orbital changes affecting incoming solar radiation are eccentricity, 100,000-year periodicity from the non-circularity, not great, but it's not exactly circular, of the Earth's orbit around the sun, from the gravitational influences of other solar system planets. The obliquity, which is the tilt of the planet. If the north always faced the sun, it would have no ice. If it always faced away, it would be solid ice. Precession, which is the wobble of the Earth, if you like, that the precession of Mercury is what showed that Newton's theory was wrong and Einstein was correct. The orbital series are obviously strongly exogenous, and both eccentricity and obliquity seem to be non-stationary due to shifting distributions over time. And that's because the configurations of other planets varies over time. Our data are at 1,000-year intervals, and let's look at them. So top left is eccentricity. You can see there's been very big cycles and quite prolonged low periods, big cycles. We've been very lucky. It's been very stable over most of the period that humanity's mattered. Obliquity, you can see, has been changing over time. It's hard to see non-stationarity in precession, but notice these big gaps here are different from the gaps elsewhere, so that's also varying. And summertime insolation, as Milankovitch calculated it, is also highly non-stationary, with two very big long cycles. If we interact them, we get a greater degree of non-cyclicality, which you can see immediately at a glance is exacerbated. Here are the actual data. The ice volume in the Antarctic is the graph A in the top left. CO2 is based on the fossil record, the ice core data in B, also correlated with data elsewhere. Temperature record is inferred from the various kinds of creatures that existed, and the sea level I don't have over a long period and won't be using. So if we plot CO2 against the negative of the ice volume, you'll see it's enormously highly correlated. If we plot CO2 against temperature, they're very highly correlated. And if we plot temperature against the negative of ice volume, the negative is just to get the two aligned rather than opposite directions so you can see them more clearly, they all look incredibly highly correlated. But there are quite important gaps in the record, as you can see, various stages where they aren't so highly correlated, particularly at the peaks. Now that raises the question, why should these be so highly correlated if CO2 levels are not actually causing what's going on? And there's a big split in the paleoliterature as to the causal role of CO2 in affecting temperature and ice volume. And the solution is that oceans hold about 60 times more CO2s in the atmosphere. The southern oceans had gigantic carbon sink during cold periods, but releases CO2 as the planet warms, as would a glass of sparkling water left standing out. So that we show, and I'll show you how we do it, the exogenous orbital variations drive temperature. That drives changes in ice, which in turn changes CO2 levels by changing the temperature of the oceans. So to resolve this, we model the three, ice, CO2, and temp, as jointly endogenous functions of orbital variables in a three-equation simultaneous system estimated by Fimmel. We're able to include all the endogenous variables in each of the equations because it's so enormously over-identified in the system. So the general unrestricted model expresses the three variables, ice, CO2, and temperature, as a function of their lag, the exogenous variables and their lag, and a vector of impulse indicators. There's a lot of mismeasurement in this process, which the impulse indicators can detect and remove, as well as some very sharp changes, for example, from massive volcanic eruptions. Lagged values capture the dynamic inertia from ice coverage. Even though periods are 1,000 years apart, that's just 1% of the eccentricity periodicity. The variables are first retained without selection when IIS is applied at 1 in 1,000, and we keep back 100 observations for forecast evaluation. 35 impulse indicators are selected, the earliest being only 339,000 years ago, mainly to maintain encompassing. Very high correlations between actual and fitted values in the VAR, and the correlations between the residuals are low except for CO2 and temp, which is above a half. The diagonals are really, it's hard to tell what the units mean, and they're all slightly arbitrary. Then we select the regressors at 1%, which gives us a parsimonious VAR X, and the indicators are insignificant in each equation are deleted in turn, and that's then modeled as a simultaneous system. And this is the outcome. So for the ice equation, CO2 and temp contemporaneously and CO2 lagged do not enter at any reasonable significance level. For CO2, ice and temp contemporaneously do not enter, and ice does not enter lagged. But for temp, CO2 currently does enter significantly, as does temp lagged, but ice doesn't. And the coefficient of CO2 in this equation at 0.008, if you multiply that by the 100 parts per million, which are the units it's measured in parts per million, that we've had since this modern era, you'd get roughly 0.8 of a degree higher. And that's approximately what we've seen from modern times. So though it's only 100,000 years back that we're using this data, it's telling us something about the modern outcomes. And very different variables occur in different equations, as well as very different indicators. The likelihood ratio test of over-identifying restrictions, chi-squared 64 is 70. The dynamic eigenvalues are 0.97, 0.86, 0.77. The first has made some people to model this as an I1 non-stationary system by co-integration. I don't think it is. It looks to me that it's non-stationary for other reasons, namely the nonlinearities and the changes over time. You cannot exclude all the nonlinear functions, and you cannot drop all the impulse indicators. So the model describes the data extremely closely. Remember, we've held back 100,000 observations, and the black solid line shows where that starts. For ice, they're very similar to the in-sample. For CO2, sorry, for ice, they're actually smaller than the in-sample. For CO2, they're very similar, but for temp, they're a bit larger. So something's happening to temperature outside what was happening historically. You can see the non-stationarity very vividly here. That's the level up to what's known as the mid-Brunhes event, and then it's much different thereafter, and that shows up in the CO2, but rather less in the ice. The results are density, the residuals are reasonably normal densities, slight autocorrelation in CO2. Two lags helps, but it makes things very complicated. It's hard to believe that CO2 2,000 years ago is still affecting what's going on, but that's what the data say, folks. So these are close-ups of the one step ahead forecast with plus or minus 2 standard errors. And they're very close until you get towards the end of the last ice age, and then they start to change rapidly. But nevertheless, the one step ahead residuals remain well within the bounds you'd expect. Interestingly, the root mean squared forecast error over that 100,000 years outside the estimation sample is smaller than the in-sample, even including impulse indicators. It's smaller, not including them for CO2, but it's larger for temp, which matched what we saw in the graphs a moment ago. So now we can run the model, since the exogenous variables are all strongly exogenous, 100,000 years ahead to see what it says about the ice age over the period 60,000 years ago, 20,000 years ago, and into modern times. And it tracks it very well until, look at that, folks. Modern times, looks like we've got a problem. It's coming outside the confidence bands that you'd expect from ice ages. Now, Ruderman argues that humanity began to influence climate by starting farming, something that Claudio's not so keen on. So we zoom into the last 10,000 years. We re-estimate the model up to 10,000 years. It still does fine. Slight increase in the coefficient of CO2 to about 1, which is still within the confidence bands. And then we look at the multi-step forecasts from then on, and guess what we see? Well, they're all well within the confidence bands, but from 20,000 years ago, there's a very systematic, if small, departure. And this matches what Snur and company have shown, namely that 20,000 years ago, proto-weeds started to appear in the fossil record, and they need disturbed soil to thrive. So humanity was disturbing the soil that far back. So let's go and do dynamic forecasts into the future, assuming the future looks like the past. So these are 110,000 forecasts from where we stopped 10,000 years ago. And they lie well within the bands, right? So that's what they look like. And they look rather similar to the kind of ice ages we've seen in the past. And the interval of the bands roughly spans the paleo range. Now we change CO2 to be unmodeled, i.e. it becomes a strongly exogenous variable, as it is currently with humanity's anthropogenic emissions. We estimate the two equation model for ice and temp conditional in CO2. The fits barely change, but the coefficient becomes crazy in both equations, and it would not be consistent with anything that happened historically. So the evidence strongly favored CO2 as an endogenous response to orbital drivers over the ice ages, jointly with ice and temperature, all driven by the orbital variables. But now that CO2 is exogenous from anthropogenic emissions, let's run scenarios of 400 parts per million where we are now, and 560 parts per million, roughly, RPC8. Now, importantly, Arrhenius in 1896 showed that log CO2 is what determines the temperature response, not CO2 linearly, as in our model. But in our model, over the ice ages, CO2 and log CO2 appropriately scaled are almost the same. But you have to adjust it into the future. You can't simulate CO2 at 400 parts per million. The equivalent of log that matches what's happened, and this has got both data sets there, is 385 for 400 and 440 for 560. And these are still huge amounts. Now what happens if we simulate it? Well, it's disastrous. We get an almost ice-free planet at the higher level, We get very low levels of ice volume at even 400 parts per million. It takes a long time to happen, but once it happens, it will take a long time to come back. So it's warning you the inertial dynamics are something you have to deal with now. And these are the peak ice age temperatures. Remember, this is the Antarctic, this is not the Earth. You need to halve these approximately to get what would happen globally. So that's about 7 degrees higher, which will cause massive, terrible deaths from heat bulb, flooding, and droughts. So what can we do? Well, modeling the UK shows what we can do. This is the UK's CO2 emissions per capita starting in 1860, which is the first observation of my data. It rises dramatically during the Industrial Revolution. It oscillates extremely violently during the First World War, the interwar period, and the Second World War. It rises to roughly the same peak, and then it dies. And now it is well below anything that's ever been seen for Britain, yet real incomes are 7-fold higher here than they were here. We've got rid of coal, that's the Climate Change Act of 2008. Oil has dropped rapidly. Natural gas has been falling, and naturally, renewables have been rising. The ratio of CO2 emissions to capital stock has fallen by 92% relative to 1860, so we're vastly more efficient, but the data are still staggeringly non-stationary. If I plot the volume of coal against CO2 emissions, it's all over the place. If I model the distributions, they're leaping around. Distributional shifts destroy econometric models if they're not taken account of, and likewise they destroy climate models if they're not taken account of. And I see very few climate models taking account of these distributional shifts. So to capture such changing relations, the model includes the two main CO2 emitters, coal and oil, capital stock and GDP, dynamics for adjustment to changes in technology, legislation, and fuel prices, impulse indicators for outliers, for the 1926 strike, etc., and step indicators for major permanent shifts, such as policy-induced. Now, steps end in the date shown, so you have to be careful to interpret them because of the accumulation of impulses, as I told you, which transform capital and GDP to logs, but keep linear, as that's where emissions come from. So impulses and steps only capture features not explained by A and B. I must be quite clear about that. They don't muddle things at all. They just remove what is not otherwise accounted for. And if you don't account for them, you can reject sound theories. So we find 3 large step indicators, and they're actually exactly identifiable with major events. 1926 is the Act of Parliament creating the UK's nationwide electricity grid that hugely increased the efficiency of electricity and therefore reduced the CO2 component from that. 1969 is the conversion from coal gas to natural gas. Conditional in coal, that greatly increases CO2 emissions, although overall it reduces them because coal gas produced more than natural gas does. 2010 follows implementation of the UK's Climate Change Act 2008 and the EU's Renewable Directives of 2009, because thankfully we were part of the EU at that stage, so adopted its directives. Now, these are not imposed policies. These have an effect beyond what all the aggressors together explain. If we test co-integration, which this data really does need, to get the disequilibrium, the equilibrium has a coefficient of 2 for coal, 1.4 for oil, coefficient for capital stocks, it's pretty big, and negative for GNP. I want you to notice that. That's estimated unrestrictedly. There's the 3 indicators. They have to be shifted in time because you're going to lag the co-integrating vector when you come to estimate the model. Now, 2 is roughly the emissions of CO2 from coal per unit BTU, and 1.4 is roughly those from oil. So they really are picking up what's going on. They match emissions. Then we transform the model to differences and the indicators to differences other than those in the co-integrating vector. And I'll just move on to show you how closely the co-integrating vector matches the actual data. ET is the data on emissions in Britain, and E tilde is the long run, and it's very close. And that's without the impulse indicators, which you can see in the residuals below are very marked, right? And this one here, of course, is the Great Recession. It's hopeless to look at what happens to the changes in CO2 because they're dominated by the 1920s and the general strike. So if I go instead to plot them in levels and I put in just the big shifts, you can see that we pick up those pretty precisely. And on the right-hand plot, I've calculated the implied Kuznets curve. Kuznets curves are nonsense in this context, but the implied one shows that indeed CO2 emissions have been falling for a very long time as GNP is rising, even although in the model GNP enters negatively. That's nothing to do with how this calculation works out. If we forecast with and without doing step indicators, if you look at the lower graph B, you can see that the dynamic forecasts from 2010 to 11 onwards are very poor if you don't include step indicator saturation to pick up the big shifts, and the confidence bands are much larger. That's these blue ones, that's a lousy forecast. And this is what you get if you forecast with the CIS, and that's the actual data over this period. If we try to calculate the 5-year targets for CO2 the government set itself, that's the data, that's the targets, we're way below, but that's the end of the good story, folks. After this, it's hard work. We've got rid of coal, that's got it down fast. We've now got to get rid of oil, gas, agriculture, construction, waste, and chemicals, and that's going to be very much harder. And we simulate trajectories out to 2050 at 5-year intervals. It's very hard to get down to those levels. It's what's going on. Now, when I'm a macroeconomist, I focus on stagnation of productivity. When I'm a climate economist, I have this huge rise in GDP per capita. And I've plotted them both here to show you just how different they are. And the answer is due to the fact that employment in Britain has increased dramatically faster than population. So if you divide GDP by population, you get a much higher value than if you divide it by employment. And that's all that's going on. So it's not that real incomes aren't rising, they're just not rising through productivity because more and more people are working and many of them are not paid very much. So what are the policy implications for moving rapidly to net zero transmissions with growth? Well, think back, forecasting the next 100,000 years from the model of ice age glaciation for 400 parts per million already shows a near ice-free planet. Now, the bit that I showed you at the beginning, where it was more stable, did actually have ice-free Arctic Ocean. And that led to massive tundra melting, which could nowadays release vast volumes of methane. That would then raise the temperature dramatically as a tipping point. It would imply very extreme weather, which is dangerous to life from high wet bulb heat. Now, wet bulb heat is when the temperature is high and the humidity is high. So you can't sweat and you just die if you're outside working. We'll get more powerful cyclones, we'll get coastal and inland flooding, and we'll get longer droughts, all of which are fairly disastrous. So it is imperative to get to net zero emissions quickly. Now, the UK model shows that climate policy has been effective. We've had a massive reduction in CO2 emissions, more than 35% over less than a decade, at little aggregate cost by eliminating coal, improving the capital stock, and renewable energy technologies. But to get any further, we need an integrated strategy. And I don't see that at the UK level, I don't see that at the EU level. The integrated strategy is if you want 100% renewables, you must decarbonize transport. And that would be crazy using batteries. It would create enormous toxic problems of disposal and recycling. The only way ahead is to use modular graphene nanotube units, which can act as electrode supercapacitors. You can then sandwich GNTs between 2 Faraday cages, remembering a car's already got a Faraday cage on top of it to stop the inhabitants in it being killed by lightning. So you'd only need to create one more. You fill it with graphene nanotubes, which are light as a feather, can store enormous quantities of electricity, and you can get viable distances, yet rapid charging. And what's important is people aren't buying electric cars because it takes so long to charge and they don't go very far. And that will remain the case if we stick with lithium-ion batteries. Now, adding to Irene's what's going to be a stranded asset, I predict that once people realize they can go down this route, all the battery manufacturers, the lithium miners, etc., will become stranded assets in addition to all those who mine fossil fuel. Now, we need to mandate cars to be plugged in when they're not being used, in which case we get a massive electrical storage system, because GNTs can also be downloaded extremely rapidly. So you then need an intelligent infrastructure of charging points that would know when your car had given electricity back to the system, not to charge you for it, but to refill it for free. And this, of course, would give renewables no additional investment storage systems, massive storage, 35 million cars in Britain alone. I don't know how many in the EU, but probably 100 million at least. So it's very easy to imagine such a system. Employment in electrical vehicle manufacture be maintained to avoid lithium mining and disposal of recycling toxic batteries. It eliminates expensive, often stolen catalytic converters, reduces palladium mining, and they're all pollutants and CO2 producers. They all go. Also, of course, it would totally destroy all those who are producing oil and gas. They would become dramatically stranded assets very quickly. GNTs are so light, they could actually power economic electric aircraft. There are already electric aircraft flying using battery power, which is utterly amazing. There are technical issues to solve, how they need insulation, that's already got several papers on it, how to make graphene, there's several papers on that showing it can be done in a flash using waste plastic. Now, how's that, folks? We get rid of plastic at the same time as we make graphene to get cars with very high storage electricity that will act as a backup system for the entire renewable structure. So it's really important to have a strategy. We could replace household natural gas by hydrogen from heating and cooking, perhaps made by electrolysis from excess renewables, plus hybrid heat pumps and solar. Backup renewable may require safe, small modular nuclear reactors. I know people go, if they hear nuclear, but they've been working in submarines for Britain for 50 years without a single accident. It's well-developed technology. It's perfectly safe. It doesn't use fissionable material. It could even burn the leftover rods from the big nuclear reactors and actually reduce the transuranic waste that would otherwise have to be disposed of. It's got huge advantages. They're not targets for terrorism because there's nothing to gain from them. You could have 10,000 of them all around the coast or near rivers or whatever, because they need that for cooling. We can certainly increase taxes as oil prices fall to facilitate a shift to all electric, and then we can tackle construction, agriculture, waste, and we need research in net absorbers. Now I get quite cross when I see things only focusing on carbon capture and storage. There are many other net absorbers. CO2 can be used to make a fuel. CO2 can be absorbed, as the Icelanders are showing, via basalt. There's many ways to do it that are much, much cheaper and much more useful. And yet all I see people investing in, and investing rather than offering a prize for developing a system, instead of leaving it open what that system looks like, as they did with, say, the Longitude Prize, they say, oh, it's got to be CCS. How do we tackle construction? Well, we've made suggestions that agriculture, fumaric acid can reduce the methane given off. Waste is more problematic. We just have to get people to be less wasteful. And that bottom line shows the article I've written with Jenny Castle, how this can all be implemented as a coherent strategy. So can humanity really change the climate? Yes, it can. Despite more candidate variables and observations, Econometrics has seen many successful applications. It's really essential to take account of the non-stationary nature of time series. There's no point in fitting a model and then testing for a break. That's crazy. You've got to do the fitting and the testing simultaneously, because otherwise the break that shows up will not be necessarily the break that happened, because all the estimates you got from fitting the model without dealing with the break will be wrong. So econometric modeling tools have been very effective in climate applications. Modeled paleoclimate data. We've modeled the forecast climate outcomes. We've modeled the CO2 emissions in the UK to find policy shifts and suggested an integrated strategy. The software is available as Autometrics and Oxmetrics 8. It's also available for free in R, and our new Excel modeler, an Excel add-in for those who can't use anything other than Excel, is available for almost nothing. Thank you.